on YouTube, and they should be fine. Let me just double check that things are okay on YouTube as well. All good. Okay, very well. So today I'm very, very excited. So, but let me see, sorry, I need to go on the page that I lost now here. Okay, just a second. So, as I was saying, I am very, very, very well excited to have Heng Yin as a professor of computer science from UC Riverside. And so Heng has been working very actively in system security over this past decades and even more probably. And he's been working primarily on system security and different aspects of system security. Like, you know, back in the good old days, it was more like a nitty-gritty systems, and now there is the acknowledgement that we need machine learning that helps us in the process. And of course, so this was also explored in the past, but over these decades, also machine learning has made tons of progress. And I guess it's very interesting to relook at what we've known and what new advances we have in the field to try if we can address a security problem in different ways. So in particular, Heng is going to be talking about different ways that we can play with representations of software, in particular binary code, for security tasks, you know, whether it is malware detection, vulnerability identification, and so forth and so on. So Heng is a professor of computer science at UC Riverside, as I mentioned. He's also the director of the Center for Research and Education in Cybersecurity and Privacy at UC Riverside. He obtained his PhD from the College William & Mary, and he's been publishing and sitting in the program committee of top-tier conferences, such as the top 4 conferences, CCS, Unix Security, NDSS, and so forth and so on. He's been receiving several awards and grants from NSF, the Defense of Advanced Research Project Agency, DARPA, as pretty much everyone knows about it, and the Office of Naval Research, ONR, and more importantly, also the NSF Career Award. And he also was a member of Coreutils, which is a pretty cool team that was in the 7th finalist of the DARPA Cyber Grand Challenge that concluded a few years ago. I'm losing track of time, so it looks like yesterday, but I know that it's been a few more years.
It's 2016, I remember.
Exactly, 2016. Oh my God! Yeah, oh my God. So okay, let's say a few years.
That's why it's so fast. Yes.
Yes, exactly. And probably from some background noise, you might have realized that my kids are back from school. So apologies for the background noise. But thank you very much for agreeing to give what I believe is going to be a fantastic talk. And it's a little bit of confirmation bias because I also am very much interested in this topic. So the stage is all yours, Heng, and please take it away.
Okay. Thank you, Lorenzo, for very nice introduction, and thank you for the opportunity for me to share our recent progress on this topic. So as you can see, the title of my talk is Learning Binary Code Representation for Security Applications. Okay. So as we can observe for the past few years, there's a surge that applying machine learning or deep learning on different binary analysis tasks. So here I just draw a very simple diagram to show how it works. Essentially, we use a binary program as the input, right? And it feeding into some kind of a deep learning deep neural network model, and it will produce some classification or inferences results. So here, the very first question probably that we have to think about is what kind of input that we need to feed into a deep learning model. Is it going to be raw bytes, or is it going to be some manually selected features? or ideally, is it some kind of automatically learned representation? So here, of course, we're going to focus on the third option because that's much nicer, that we don't have to manually specify, and also it provides much richer, semantic information than just raw bytes, right? Of course, in terms of the problem space, you can use this kind of workflow to to tackle all kinds of security problems, such as malware classification, vulnerability detection, and some other reverse engineering tasks, such as function argument inference, type inference, value set analysis, such and such. So in terms of the representation learning in other domains, I mean, for people who have worked on machine learning, I guess you have more or less familiar with, for natural language, we use some kind of word embedding, such as word2vec. For image processing, there are things like kernels or filters that can actually we can put on top of the pixels to extract higher level features from the image pixels, right? So the natural question we're asking here is that what kind of representation that we should have for binary code, right? So here I showed you an overview about what I have done in the past few years, starting from 2016. So it's in terms of this workflow, I'm showing you here. It started from the disassembly. Okay, so I'm not going to feed just simply raw bytes to the the deep learning model. I have to disassemble the binary such that at least I can give you instruction level information. So, but disassembly by itself is already pretty hard, okay, for binary code. So essentially, the very first thing we need to think about is a good disassembler. That has to be very, very fast, because remember that deep learning needs lots of data, right? So you need a huge amount of data, and you have to process them. The first step is to disassemble the binary code. So the binary code disassembler must be really, really fast. Of course, has to be also very accurate. So this is the first thing we need to do. And I showed you our recent publication, Usually Security 2022. It's a deep learning based fast disassembler. And then the next thing is that, what about instruction representation, right? So we need to somehow learn a representation for instruction. And to show you some related work, of course, the very first thing you need to think about is that maybe I just directly apply word2vec, okay? So I treat the tokens from the instructions from an instruction as a word, and I directly apply word2vec algorithm to learn embedding. That's a very straightforward idea, and many papers actually have used this idea. And the other one is ASM2vec, which is you can treat it as a variant of a doc2vec, applied that it's applied to assembly code. And recently we have published a paper called Palm Tree in CCS 2021. Essentially, we propose an assembly language model based on BERT that learns the instruction representation. And then on top of that, we have we know that a group of instructions consists it's a basic block. So can we learn a representation of a basic block that takes into the context of that basic block, which means the nearby basic blocks in the control program. Okay, so by doing so, we can essentially do binary code diffing at the basic block level. Okay, so I also showed you some basic schemes. For instance, some people have used just simply sum up instruction embeddings that for the basic block to simply produce the basic block embedding. And there's a work from NDSS 2019 called InnerEye that use a transformer to directly learn a basic block embedding from the instruction tokens. We had a paper called DeepBinDiff, published in NDSS 2020. Essentially just does what I just said, learns a contextual, context-aware basic block embedding for binary code diffing. And then last, we talk about function embedding. And then I have two papers, and that's Genius, which is probably the very first paper we start to seriously look at applying machine learning on binary code analysis. The idea is more traditional kind of machine learning approaches. We use codebook, vector condensation to essentially produce an embedding for a function. And we use vulnerability search as a security problem, essentially that's to drive this research. Okay, so a year later, in CCS 2017, we published Gemini, which is a graph neural network approach to learn function embedding. Interesting, you can see that even though in terms of workflow, we have to produce, when we build something like an architecture, right? So we have to build something from the lowest level and then gradually up and up, right? So as you can see, we need to talk about disassembler, talk about instruction embedding, basic block embedding, and function embedding. But if you look at this timeline, we actually start from function embedding to begin with, and gradually move down to basic block embedding. That was 2020, and then instruction embedding, and in the end, disassembly. So I just want to share with you, we'll kind of look at this problem somehow in a retrospective manner. But in the end, we would like to show you at least one idea, one design that we have for this whole binary code representation learning architecture. So, like I said, at the very first, we look at the function embedding, because at that time, like 2016, 2017, we were thinking about, this vulnerability search, mainly because of the code clone, right? So function embedding, the idea is that we would like to try to learn a numeric vector or embedding for a function such that two functions that have the same semantics, same IO behaviors would have similar embeddings. So their distance is short, and such that these two functions with similar, also two functions with different semantics will have this similar embeddings. So if we have this kind of property, then we can conduct a very scalable and efficient search in the embedding space for vulnerabilities. So that's essentially the very initial idea that drives this research. So obviously, there are, in addition to vulnerability search, this also have other applications such as plagiarism detection, malware provenance detection, and so on. Okay, so I just want to show you there are other kinds of applications, but fundamentally, the idea is to learn a function embedding. At that time, around the 2016, 2015, there have been a few papers that essentially perform graph matching to identify vulnerabilities. Okay, I just showed you the two papers. One published in Oakland 15, and the other one is NDSS 16. So the whole idea is to perform graph matching. Of course, the features that extracted for each basic block is a little bit different, but the whole idea is about graph matching. Okay, I just showed you roughly the workflow here. Essentially, you have an input control flow graph, and you have a database of lots of control flow graphs, And then you have this kind of search engine, and such that you want to find the most similar control flow graph that is most similar to your input graph, and they can be the candidates of, say, vulnerable functions. The problem here is that the graph matching is a bit hard problem, and the most efficient algorithm is about n cube. It's already very approximated algorithm, right? So if we have to do this kind of matching one by one, it's going to be extremely slow. Okay, so that means the scalability is a problem. So that's why we propose this approach that learns the function representation, such that in this case, as you can see, we have the same kind of control flow graph as inputs. We call it attributed control flow graph, ACFG, and we feed it into this embedding network, and it's going to produce this embedding. All right. At that time, we use this this model from ICML 16, for this embedding network. Okay. So this is essentially some manually selected features, okay, that we kind of borrow from prior work from NDSA 16. Okay. Again, so let me just repeat that we work on this problem in the reverse order, right? So work on the function embedding, but later on we actually look at how to automatically learn the representations for basic block, for instructions, and so on. So such that the whole workflow becomes even better, right? So this is an example of a CFG. So from the left-hand side is a CFG, and then we extract these features, becomes a CFG. The goal is to learn numerical representation from this ACFG, and and then this is essentially the training process. We use the Siamese architecture. So essentially, we have two identical network. All the weights and parameters are shared, and we feed in a pair of inputs. In this case, a CG1 or CG2. And the goal is to such that we compute the cosine similarity, and based on the input pair we provide, whether it's a positive or negative, and then we want the loss function to be close to 1 or -1. So that's the way we learn such input representation. So as you can see, the application independent pre-training essentially compile the source code into different platforms, different compilers or compiler options, and then a pair of binary inputs compared from the source code is labeled as +1, otherwise -1. Okay, so this is a CMS training. And of course, we can also have application dependent retraining, such that human can label some similar or dissimilar functions to essentially fine-tune this model. Some closer look about this embedding network. Okay, so essentially, initially each vertex has an embedding vector computed from each block, and then in each iteration, the embedding on each vertex is propagated to its neighbors, and after the last iteration, the embedding of all the vertices are aggregated together, and then a transformation is applied in the end to compute the embedding of the graph. Okay, I mean, this is one kind of implementation. As you probably realize that you can apply many different variants of graph neural network that more or less achieve the same goal. So this is just some closer look about the propagation layer. Essentially, matrix multiplication plus a ReLU as activation function, and then there's also like n layers of nonlinear transformation. Okay. So why deep learning, deep neural network? So it's actually high. First of all, it's high efficiency compared to the work we have done in 2016, CCS 2016, this approach is much more efficient, okay, because the vector and the matrix computation can be easily accelerated by SIMD instructions and the GPU, okay. But compared to, I mean, in 2016 paper, it's still some sort of graph matching, and it cannot be easily parallelized. High accuracy, the training is end-to-end. Well, at that time, applying end-to-end training is good, but nowadays we can have seen a trend to apply layers of pre-training and fine-tuning that achieves even better results. Okay, and no graph matching algorithm. Okay, so essentially here it means that we don't need to manually provide a approximate graph matching algorithm like a bipartite graph matching or some other algorithms. Essentially, we rely on the deep learning to automatically learn how to match two graphs. Okay, so that's the pretty interesting insights. So here we show some comparison about how good it is. So Gemini compared to BGM, which is bipartite graph matching algorithm that the previous papers have used, and Genius, which is the a codebook plus vector quantization idea. As you can see, the Genius is better than the BGM, which is bipartite graph matching in terms of accuracy, and the Gemini is significantly even better, okay, in terms of accuracy. Serving time, which is in terms of the processing, the instruction, I mean the embedding generation time, okay, Genius is about a few seconds to a few minutes, okay, for one function, depending on how large the function is, right? So with this deep learning approach, it's only a few milliseconds. So you can see the acceleration is multiple orders of magnitude. So from 2,500 to 16,000 times faster. Training is also much faster. So a Genius is about more than a week sometimes, but here it's only less than 30 minutes. So the efficiency you can see is greatly improved. So here it shows the case study in terms of vulnerability search. We can essentially conduct the same kind of experiments for searching firmware images, searching a few vulnerabilities in firmware images, and we can have the same experiment for Genius and Gemini, and we can see after retraining the recall is much better. So as you can see, 42 out of the top 50 functions are confirmed vulnerabilities. On previous work like Genius, only 10 out of 50. Okay. So after our Gemini paper is published, October 2017, there are many researchers kind of follow this idea. Oh, embedding generation. Let's improve this. Try different ideas to generate embeddings for functions. So by the way, so this paper becomes really popular. We have received 365 citations by yesterday when I check it. So I just give you a few examples. So ASM2VAC, which is published in Oakland 2019, and INERI, which is in NDSS 2019. There's also a follow-up work by Google, Project Zero team. I found this quite interesting from their blog, so I just want to share with you as a screenshot. So as you can see, this blog is published in 2018 December. So they said, okay, searching statically linked vulnerable library functions in executable code. And then they have this paragraph here. So on the side of academic research, several interesting papers, so CCS 16 and 17. These are the two papers I just, my papers that I just mentioned, in a few slides back. So propose the sophisticated machine learning methods and blah blah blah. So essentially, they are interested to kind of follow this this idea, but apply I guess what they call it will be like more straightforward idea in using some more classic methods, machine learning methods. So they call it the function sim search, and they also show some some successes. So I felt it's quite interesting. So we actually asked my students to do some evaluation as well. So here I show some comparison. And in this case, I specifically compared Gemini with a function sim search and ASM2Vec. Okay, so in terms of so here in terms of the efficiency, as you can see, ASM2Vec is much slower. Okay, it's much slower, as you can see, so down here. And function sim search is around in the middle. Okay, but Gemini is way faster. Okay, so the efficiency wise, of course, Gemini beats the other two approaches. In terms of the I guess this is about generation. So this is about efficiency of a generation. In terms of the efficiency of matching, so in this case, because ASM2Vec is a kind of slow, we cannot really draw these nice figures. So we only draw the figures for Gemini and function sim search. Again, so Gemini is much faster than function sim search. Okay, so accuracy wise, this is across compiler optimization levels. So we showed you the ROC curve and the recall rate. And in this comparison again, so Gemini is better than the other two. Okay, so it also showed you the accuracy between x86 and x64. So again, the same trend, but the gap is even wider. So essentially, this up to this point, I showed you our efforts on the function embedding. So after that, we were thinking, what about a finer granularity embedding, which is basic block embedding, and the kind of the driving application is binary code diffing, right? So we all know, BinDiff, which is a tool that does the binary code diffing, and it applies, graph isomorphism kind of matching with lots of heuristics. Okay, so the natural question is that, well, can we do it better, right? Can we apply somehow more principled machine learning approaches to tackle this problem? Naturally, if we can learn a good basic block embedding with some graph matching algorithm, doesn't have to be a very nice one, a very fancy one. It should outperform, we hope, the traditional kind of a BinDiff approach, right? So the idea we had is that we learn this embedding again. So for each basic block, and we would like to capture both block level or inter block features and inter block features, which is topological features in CFG. So with this algorithm, kind of a network representation learning algorithm. Of course, there are a bunch of them, but here we use DeepWalk. Okay, so here is an overview about this approach. Essentially, we're giving two binaries that we like to diff, and we generate a control flow graph and token embedding for both binaries. And we have to generate interprocedural CFG, and for token embeddings, for basic block token embeddings, we'll use some like a doc2vec model or ASM2vec model to generate this feature embedding. And then to learn this interblock representation, we use this variants of a deep walk. We call that called TADW. It's a I think it's a text associated DW deep walk. Essentially, it combines essentially the block level feature and topological features together and learn the final embedding. And then based on this kind of representation we learned, we can use a pretty naive in terms like a greedy algorithm for matching basic blocks. So there's some details about how it's actually done, but I guess I don't want to spend too much time. I guess if you're interested, you are welcome to read the paper for details. So essentially, I just want so I'd like to share some results here. As you can see, we compared DeepBinDiff with BinDiff, and also some other variants. For instance, DeepBinDiff minus context. Essentially, we're not going to use deep walk algorithm, just some simple text learning algorithm, just the inter-block embedding features. Okay, so with that, how good it is, right? So I will also use ASM2VEC as algorithm, just apply graph matching, K-hop graph matching. Okay, so as you can see, the trend is pretty clear. So all the other variants and also the BinDiff algorithm performs much worse than this kind of approach than DeepBinDiff. So more evaluation, as you can see, the trend is also similar. Okay. So yeah, essentially that was done in 2020 NDSS, and afterwards we're thinking, well, can we do look at instruction embedding, because it becomes so fundamental, right? So if we can learn a better instruction embedding model, it will benefit all other downstream binary analysis tasks. Okay, including binary diffing, including vulnerability search, and so on. Okay, so this is essentially our work published in CCS 2021. It's a palm tree. So essentially, we're learning this assembly language model for instruction embedding. Okay. Doing in terms of time. Okay. So background. Okay. In terms of the input choices, so there have been quite a few papers that apply some simple ideas, such as raw byte encoding. Okay. So for instance, this alpha diff paper directly feed raw bytes into the deep learning network. Essentially, just hope that the deep learning network is so model is so powerful, you can still learn a lot of meaningful things out of raw bytes. Okay, one-hot encoding, which is pretty standard practice in machine learning, right? So I just convert each byte into this 256 dimensional vector. Okay, actually, a bunch of papers has used this idea. I guess one downside is that it doesn't really provide any semantic level information, and if it does, then you have to rely on very sophisticated, expensive machine learning model to hopefully can learn some semantic information out of it, which is really questionable. And then manual encoding, okay, of the disassembled instructions. So for example, there's a paper called Instruction2VEC, which has some kind of encoding idea. In Gemini, when I say manual encoding, it's not really manual encoding. Essentially, it's about extracting some features. For example, like the counts of arithmetic instructions, floating point instructions, the counts of constants and the strings as features. Not really encoding of at the instruction level. Okay, expert knowledge. So yeah, so if expert knowledge is good, then maybe your downstream applications quality is good. Otherwise, it may not be that good. So it's a really tedious and maybe error-prone process. And then in terms of learning-based encoding, so like I said early, word to vec, you can directly treat instructions as a instruction as a word, function as a document, to kind of learn the instruction embedding. This actually, many papers have taken this approach. Okay, and doc to vec, in this case PVDM. So ASM to vec takes this approach. In this case, it treats an instruction as one opcode, two operands, so kind of formats, and then so to learn the the embeddings actually at the token level. Okay, so you can carry higher level semantic information, hopefully, right? However, there are some challenges that this approach, in particular ASM to vec and its word to vec, didn't address. So first of all, instructions are actually complex and diverse. So especially true for x86, instruction sets, right? So we know that. I just give you a few examples here. So you may have very complex expression, right? Or you may have, in this case, 3 operands, not just 2 operands. And it may have implicit operands, like E flag is implicit operands. You may have prefix and implicit operands in this rep move SP instruction. And then the last one, essentially, E flag is an implicit input operand. So how can you expect these learning algorithm can learn all these kind of complexities automatically? All right. So just a few examples. And number 2 challenge, instruction can be reordered. Okay. So a compiler does that all the time in order to improve the efficiency, right? So in this case, I just show you one example, right? So move, call mem copy. So, and the return value is stored in REX. And you can see that this move REX, RCX, REX, and later JE, and so on. So you can see that there's a gap between these 2 instructions. And then the test RBX is, kind of inject in the middle. And then the, JE instruction that actually use the outputs of text is, again, 2 instructions away. So if your learning has to rely on this context window and the instructions can be frequently reordered, then the learning cannot be very good. So that's the another challenge. So to address this challenge, these challenges, we propose this pre-trained assembly language model. Okay, so it's based on the BERT model used in natural language processing, but we introduced 2 additional training tasks to tackle these challenges. Essentially, as you can see from so we still have a context window here, but we're going to construct the DFG, the control flow, the data flow graph, and then we sample this graph to come up with data flow pairs and the control flow pairs. Okay, and then we feed these pairs into, of course, we'll tokenize the instructions, and we feed it into this BERT model. Okay. And then we have 3 downstream tasks, MLM, which is a default training task, and we have a context window prediction and a depth use prediction to essentially stimulate and push for better learning results. So, so here I just want to share you some evaluation results here. As you can see, how much impact it has on the downstream applications. So I just mentioned the Gemini, right, which is a graph neural network and use the manual selected features, right? So as you can see on this side, this is the original model, right? Manually select a vector, design a vector, and feed into structure to vec model, graph neural network model, and we kind of replace these part with the instruction embedding that we learned with a simple min pooling, layer, and feed into the structural back. Okay, and then we kind of showed you the comparison results for Gemini. Well, we may see that, oh, these kind of curves seems to be much lower than the ones we probably showed earlier. The reason is that we use completely different test set than the training set. Okay, so we like to test how general the learned model is. So we want to see so essentially a more challenging data set for evaluation. But in this case, we can see that original Gemini is around here, which is not very bad. Okay, some other approaches like one hot, word2vec, ASM2vec performs even worse. Okay, and if we look at palm tree and different variants or palm tree that takes away some features, they are more or less similar to the original Gemini, but the final version, performs better than Gemini. So we can see that with a better instruction embedding, you actually improve the results. This is another example that shows the downstream application of palm tree. So EKALAVYA is a function type signature inference work. Okay, so the original model is here. As you can see, this also it uses word2vec and feed into this GRU layer. Okay, and then we replace this word2vec with our instruction embedding, and we see how it goes. Of course, we also tested some other embedding approaches. Okay, so like one hot, instruction to vec, so ASM to vec, so on. So as you can see, some of these embeddings performs really poorly. Okay, like one hot and instruction to vec. Word2vec performs okay, but it's worse than ASM to vec. Again, so ASM to vec is worse than palm tree. So again, you can see that with a better instruction embedding, the downstream model's performance can be further improved. So this is another downstream task called DeepVSA for coarse-grained value set analysis. So we can see the similar trend that by replacing this input layer with our instruction embedding, the palm tree, so here's the last row here, we can see that performs consistently well in different categories of memory regions. So compared to the original DeepVSA, okay, you can see that DeepVSA is only good in terms of the globals, the precision, which is good, but all the others cannot beat our palm tree version. Okay, so the last one I want to share with you is the disassembler. So as we can see, essentially the very first step is to produce the disassembly from the binary codes, and then you can learn embeddings for different kinds of categories of binary codes. So so this paper published in Usenet Security 2022. Okay, essentially it's we learn a relational graph convolutional network model on instructions for fast and accurate disassembly. So here I give you I show a quick survey in terms of different disassembly approaches. So traditional one, okay, traditional approaches like a recursive or linear disassembler. Okay, so we can achieve nearly 100% accuracy on regular files, but it can be very slow and also vulnerable to obfuscations. So in terms of the speed, it's probably about 10 to 200 kilobytes per second. It doesn't support GPU that easily. Superset disassembly is approach for binary code rewriting. It's really fast and no false positive, but it has a huge amount of false no false negatives, but very high false positive because the application is different, right? So for rewriting, not for accurate disassembly. So and then there are like a probabilistic disassembly and the data log disassembly, which were published recently. So for example, probabilistic disassembly has almost a no false negative and a little bit false positive, but it's kind of slow, only 4 kilobytes. Data log disassembly about 100% accuracy, but kind of slow. Okay, so interestingly, there's also another deep learning based approach called XDA, which used the transformer model. It also close to 100% accuracy, but it's pretty slow, actually much slower than other approaches, only 140 bytes per second, because the model is very complex. And DeepD, our work, can achieve very high accuracy. And if we look at the GPU, can be about 25 megabytes per second. So it's really good for large data kind of processing, training and testing. So this is a overview about the DeepD model. Essentially, we take the raw bytes as inputs, and we quickly disassemble every possible byte offset, and then produce a superset instructions. Okay, and this is done in GPU, which means it's a greatly parallelized. And then these possible instructions, all possible instructions, are kind of converting to some instruction metadata according to this opcodes and the monogram and so on. Okay, and then this metadata is fed into these network. So instruction embedding network, number of RNN layers, and then this original convolutional graph convolution network. And then we use a sigmoid for classification. So in the end, you can classify true instructions versus false instructions. So that's the whole idea about this deep learning based disassembler. So by doing so, as we can see, the efficiency is greatly improved over the traditional approaches or other baseline approaches. Let's look at this, right? So IDA Pro is around here. Okay, so this line is here, about like 10 seconds or so on average, right? So Binary Ninja is another kind of a disassembler, Ghidra. So you can see they're all around here. So this is the middle part, middle region. Data log disassembler, which is a bit slower, right? It's around here. And then XDA, which is another deep learning based approach, is very slow. So this is CPU version is here, and GPU version is somehow comparable with IDA Pro. Okay, DeepD, so CPU version is actually better than IDA Pro other disassemblers, and GPU version is way faster than other approaches. So let's look at generalizability evaluation. Of course, accuracy is always good, right? But we have to challenge this model, which is how general it is when you see previous unseen binaries from unseen compiler. So how do we do it? So how well can we do? So specifically, we compare with DeepD, compare DeepD with the XDA. As we can see, the generalizability is much better. The accuracy is for this instruction level and the function level is much better than XDA. So sometimes you can see the XDA's accuracy is pretty low. So only like say 0.4%, right? So it's really low. And then we also look at obfuscation, right? Why we look at obfuscation? Because if you want to apply this for malware analysis, malware detection, obfuscation is often, applied to binaries. So in this case, we just show you one result that we use obfuscator provided by Lin and Debray. So we can see that for this data set, we still perform constantly well in terms of precision and recall. But the other approaches, for instance, like IDA-Pro and Ghidra, so you can see the recall and the precision greatly dropped. But also it takes much longer time to process. For example, Ghidra takes about 10,000 seconds to produce, to process it, because it's misled and confused by the obfuscated binary. So, but in our case, we perform constantly well and very fast. So its impact on malware classification. So the idea is that if we can produce disassembly results so fast and so accurate, so how much is the impact on the downstream malware classifier? So I just show you the two evaluations. Malcom is a convolutional network that people have proposed in the past. So on this data, Microsoft malware classification dataset, it performs generally well. If its malware is not produced to evade the classifier, right? So it's only on original data sets. So Gemini, in this case, we just created such a still pretty naive deep learning model. In this case, we use Gemini to generate function embedding. The original Gemini, not the really improved with the palm tree version. Okay, original Gemini, and plus min and max pooling, and with this multi-layer perceptron as a classifier. Okay, so we can see we can achieve almost the same kind of classification results in terms of training accuracy. Slightly lower, I would say, but the testing loss is slightly lower than the Malcom model. Well, I mean, it's not a great improvement, but it just shows there's a promise if you design a better deep learning architecture based on the embeddings we generate, it might be much better, right? So another evaluation we have for Ember, which is using a decision tree as an algorithm. So we showed you that with additional code features that we produce using our disassembler, we can improve in terms of training accuracy and testing loss. So you can see the testing loss almost cut in half. So it shows some good promises here. Well, in summary, deep learning is really a powerful tool for binary analysis. Okay, we have showed you a few papers we published to address different problems and so on. And in somewhat retrospective fashion, we showed you that we can build a good pipeline that starts with a fast and accurate disassembly, and we can produce better instruction embedding, and on top of that, you can generate better basic block embedding and function embeddings to address different downstream binary analysis applications. So with that, I conclude my talk, and I welcome your questions.
Thank you, Heng. So let me just give you a round of applause, like a small icon there, and this virtual round of applause until we, we still go back to in-present seminars. So that was very interesting talk, and let me just see just a second on YouTube if we have any questions so far, so that I can also stop the streaming. So let me just stop